This video is about the Euler update numeric method of modeling especially nonlinear dynamic situation systems of differential equations. A famous case of which are the Lorenz equations, the weather modeling equations. I wanted to do some fun numeric math that, well, is what I like to do. Let's just go through the Euler update and the Lorenz equations. Euler's theory of how to model equations numerically is that for sufficiently close together, time 2 and time 1, a function evaluated at time 2 is roughly the function evaluated at time 1 plus the time difference times the time differential evaluated at the function at time 1. Get some dependencies. We can pass things as arguments. Amazing. The Lorenz equations, so the weather-like equations, for some initial conditions x, y, and z, well, it just happens to be this series of equations, and you can see these nonlinear terms, this x times z, and this x times y over here. So we set some initial values, and just for some number of generations, we just do the time update for that step based on Euler update approximation. Then we're going to plot the chaos butterfly, which is the, what do you call those? That is the trajectory of the Lorenz equations for those initial values. So we've looked over that. Cute little program. I think I'm too cool for Python now, but can't beat expediency at this particular point because I wanted to churn out another video. So let's just run that. So using a virtual environment. And then that's Python lorenz.py, and for some reason I know to pick 10, 10, and 40 for some initial values to try, though this, what we'll see, is robust across a couple of different initial values. If you think about those equations, they have two I should have swatted up on my terms. They have two attractors, but neither of them will win. They're both unstable attractors. The time delta should be something small, and generations can be something large, and the output name can be my butterfly.png. Alright, and let's beautiful. So if I were better at this, I would have plotted the two what do you even call those? Not poles. Well, the 2 points that it's the two unstable, those are, God, tip of your tongue. Get these from a matrix. Eigenvalues. Well, those things anyway. Thank you.